So thank you everybody for joining. This is one of our IPC Education Foundation career and technical webinars. So the point of these is to bring various interesting, relevant technical topics somewhere in the realm of what IPC does. So our audience today should be either some college students, some high school students. We might have career and tech classes from either high school or college. Most people on, I believe, should be in high school, but we will see. Feel free to post in the chat where you guys are from if you are interested. I'm going to be behind the scenes for most of the webinar. I'll answer chat questions, moderate some Q&A. So what I'll do is introduce Patrick Crawford in just a few moments. If you have any questions, you are welcome to post them in the chat. You're welcome to post them in the Q&A. And later on, after Patrick is done giving us an overview, we may open up for some Q&A. If you are interested in actually asking the question yourself, go ahead and raise your hand and we'll have you unmute. But you're also welcome to obviously just use the chat or use the Q&A. Let me introduce you. So Patrick Crawford, he is the manager of design standards and related industry programs at IPC. Patrick manages the IPC 2581, which is generic requirements for printed board assembly products, manufacturing data and transfer methodology. Some other standards, let's see, around materials, substances, lab reports, responsible minerals sourcing, very technical, as you can see. Currently the liaison for the Design Community Leadership, Industry Leadership Group of IPC Design. Let's see. Patrick has also served the printed board design industry. He has his master's in materials science and engineering from Portland State University, where his studies focused on the growth of nanoscale carbon allotropes for use in next generation memory devices and novel biomedical applications. Quite technical. I'll let you explain anything there further and take it away.
All right, thanks everybody. I really appreciate everyone joining today. Obviously some technical issues that I'll try to work through, but I'm looking forward to speaking with you all about something that I am very passionate about, which is 3D printing. I have been using 3D printers for almost a decade through research. In undergrad, I was a founding member of the 3D printer lab at my college. I spent many hours printing for various research projects around the school, building housings for lightning detectors and tools for agronomics research. When I was in grad school working on the systems to grow the carbon allotropes, specifically vertically aligned carbon nanotubes and graphene, we designed and printed a lot of components that went into those systems. And now with IPC, I have the fortune of working with our two resin printers that we have in order to make trophies for our committee members. So I'm very fortunate and happy to be here. I'm going to share my screen really quick. If you're just joining, unfortunately, the slide deck that I was going to present got corrupted in the crash. I have a backup slide deck that is unfortunately not necessarily tailored to careers, but I will speak to them as if they were. So give me 1 second to share my screen and we will get going here. Screen 2, share sound. All right, let's go and let me present slideshow and present from the beginning. Okay, great. So 3D printing for fun and profit was the working title I had the last time that this was saved. It should say 3D printing for hobby and career, but it is what it is. So my goal today is pretty simple. We're going to spend some time talking about how 3D printing is alive and well in many industries today, and how within those industries there are all sorts of applications that you can become involved in as a career. But in my opinion, at the basis of all of that is a love for additive manufacturing that comes from starting as a hobbyist. So a lot of industrial machines and systems, they don't necessarily scale well to the garage level. I've heard of one or two, but most people don't have a reflow oven for soldering electronics in their garage. It's even harder when you're working at the systems level. The Industrial engineering level, you can't put a full assembly line in your garage. But fortunately, the theory behind most industrial scale additive manufacturing technologies that we'll talk about do scale well to the desktop and hobby level printers that you yourself can purchase and experiment with. So coming away from today, I want you all to feel a little more empowered and comfortable with picking up a printer. And we'll talk about how expensive that is, how hard that is. And the answer is within, obviously there's a range of prices for printers. It's not that bad. Okay, so an overview of what we're going to talk about today, or at least as close to an overview of what we're going to talk about today as this slide deck is going to give us. We're going to do a overview on what is 3D printing. We're going to do a little bit of a history on 3D printing. We're going to give an overview of the various 3D printing technologies and their applications and potential career paths you could take within them. I am going to do a deep dive into fused deposition modeling printers. This is one of the hobbyist accessible printers that you can get started with. And then I'm going to do another deep dive on vat polymerization, SLA, DLP, and some other letters we won't worry about right now. And those are also hobbyist accessible. I'm not going to do this demo on our printers. I'm going to be showing videos throughout, though, that kind of highlight what the different technologies do. But I will be giving some printer recommendations so that you can get started. All right, so super high level, I'm going to assume that no one here has ever seen a 3D printer before or know what a 3D printer is. You're walking out of the cave, Plato's cave, and out of the darkness, right? So very generally speaking, a 3D printer is anything that creates 3D objects via the sequential layering of material that is usually adhered to a substrate, or it should say, is suspended in a vat or a workspace of a similar material. And we'll see what that means. And say, no, additive manufacturing can include etching and deposition. And I say, I've never heard a chemical deposition system referred to as a 3D printer. But you're going to hear it used interchangeably. A wide range of industrial applications, way too many to include on one slide. We'll get into them, but suffice it to say that it is useful from prototyping all the way through production. So there are three major branches of 3D printing, the arterial, labels, if you will. Fused deposition modeling, or FDM, is when a solid material, either a filament or pellets, in very rare instances pellets, is fed through a heated extrusion nozzle. You can see here, the nozzle is depositing Yoda's material as he's being printed. Powder bed fusion. Powder, usually a polymer or a metal alloy, is selectively fused via laser. So you can see there it's being rastered back and forth. It's actually fusing the powder together. That's a metal powder. In that case, it's metal powder. It doesn't have to be metal. And then UV polymerization. So SLA, DLP, again, we'll get into those initializations. A liquid precursor is cured or hardened by an ultraviolet light source. In this case, there's an ultraviolet light below here, and it is hardening kind of as it moves up. Just this here. Okay, so I think it's really important to give a context of 3D printing, the history of 3D printing, just to impress upon all of you how rapidly the last 5 or 6 years, 10 years, have seen the proliferation of desktop 3D printers, hobby level 3D printers, and then on the industrial side, the reduction in cost. Most of the time, some of the systems they have now are like way more expensive, but in general, the reduction in cost of these industrial scale machines that perform additive manufacturing. So in 1981, the first rapid photopolymer prototyping system was conceived of, the patent was filed, but it wasn't until 1988 that the first one was actually built. So it took almost 10 years just to even build the thing. And here you can see that tiny little bit right there is the workspace. So how little volume they had to actually print. In 91, Stratasys, which is still around today, we'll see their name, or you'll hear their name quite a bit. They patented the first fused deposition modeling system. So to remember the one that was building Yoda. And that, again, it's like that tiny little volume in there to print, and that massive refrigerator washing machine. And then in 1997, Aeromat patented and sold the first selective laser sintering machine to fuse only one metal, which was titanium alloys. That's it, no other metals. So up until that point, the average cost per unit, industrial, or I guess at that point there were only industrial, there were no hobby units yet, was about 40 grand, and that's not adjusted for inflation. In 2005, the RepRap project launched. The way that they got around the Stratasys patent on FDM was they actually just said, here's some instructions on how theoretically one could build a printer. Have fun. And then most of the parts were off the shelf. Some of the parts were printed by other printers that your friend might have. And then the control boards, which were not patented necessarily, were sold by RepRap or by authorized distributors. However, in 2009, that patent did expire, and a couple of different things happened all at once. Thingiverse debuted. MakerBot released the first, like, this is a 3D printer that we are selling kits. And in 2014, similarly, the SLA and the SLS patents expired. So since 2014, I guess that is 8 years ago now, the explosion in consumer level 3D printers of all flavors and the industrial explosion of 3D printers of all flavors have been due to these patents expiring. And now the average cost of printers, granted taking into account kind of a wide variety of consumer level printers anyway, is only about 350 bucks, with bigger build volumes and better quality than any of these industrial machines in the 80s and 90s ever had, give or take. What I'm not going to mention is all of this that has happened in the history of 3D printing. Scan this, Google something if you want. It's insane what has happened. A couple of highlights: the 3D printed gun controversy that is still ongoing. Who owns files, right? If I put a file on Thingiverse and then you print it and then you sell that print, do I own it? The answer is no, but similar IP issues. And then all sorts of fun advances in the space of 3D printing. Okay, so like I said, there's three arterial branches of printing: FDM, UV, and then powder bed fusion. Within those, though, there are distinct technologies that have different applications. FDM is kind of just its own stub, I guess, its own truncating artery. There's different kinds of FDM printers, but it's the same basic technology. UV does have a few different branches, though. They have SLA, which is stereolithography apparatus or apparatuses, digital light projection, which is DLP, and then material jetting, sometimes referred to as MJ. In powder bed fusion, there is selective laser sintering, or SLS, direct metal laser sintering, DMLS, or electron beam melting, EBM. There is also called something, it's selective laser melting, which we'll talk about, and then binder jetting. So of those, and we'll talk about these at the end, if you want to get involved in 3D printing, the hobbyist accessible technologies are going to be FDM, some SLA units, and then a lot of DLP units, or a flavor of DLP that we'll talk about. Okay, so the first technology that we're going to talk about is a powder bed fusion offshoot called Binderjet 3D printing. So this is a technology that operates very similar to an inkjet. So an inkjet printer, there is one line of ejectors that will eject ink strategically, kind of so it can make an image. This does the same thing, but instead of printing onto a piece of paper, it prints onto a layer of powder, either a metal powder or a silica powder, or even some kinds of ceramics, a lot of times polymers, and it will spray a glue. And then that layer will drop down, and then another layer of powder will be pushed over, rinse and repeat. So you're actually gluing layers of powder together. There are some upsides to this. So this is a low to no heat process. Oftentimes, the more variables we have in a system, especially a complicated system like this, the more prone to failure it can be. Without heat profiles to worry about, ramp rates, all of that, you have less failures when you're actually printing. This is, however, almost exclusively used for industrial applications. Kind of makes sense. It's very power consumptive. It's a big unit. We'll take a look at a video in a second. Like I said, different materials. We're not going to worry too much about the actual characteristics of the machines, but suffice it to say they can be pretty crude. It's not as fine as some other technologies are. That's right. Forgot that my PowerPoint is misleading. It's truncated here. So we're going to take a look at a video of Binderjet manufacturing, just so you can see what it looks like when it's running. So let me go ahead and pick it up. All right.
Guys, this is using pretty similar technologies as what we've already talked about, but I want
technology of inkjet.
Aaron, is my sound coming through?
In this process, a liquid binder is selectively deposited on a powder bed with a print head. It is a growing process that allows the production of parts for the manufacturing, medical, and dental industries. This technique enables the production of metallic and ceramic parts, as well as sand molds for castings. To start the process, a 3D drawing is imported into the printer software. The powder to be used is placed in a dispenser, which ensures a constant supply during printing. First, a powder layer of a specific thickness is spread. Thereafter, the printing head, moving on 2 axes, projects the binder where necessary. Before moving on to the next layer, the solvent contained in the binder is evaporated by an incandescent lamp. The powder bed is then lowered and a new powder layer is deposited. Therefore, the production takes place in a series of steps that build the part layer by layer. When the cycle is completed, the binder is cured by placing the container in a furnace. The temperature and time depend on the type of binder employed during printing. After this step, unbound particles are removed to reveal the part or the mold. After this step, the sand molds are ready to be used in foundries. The metal and ceramic parts must undergo sintering, infiltration, heat treatment, or hot isostatic pressing before being used.
All right, so you have these post-processing steps that are necessary with binder jetting that aren't necessarily aren't needed with other types of 3D printing technologies. Okay, cool. So this is awesome. You can do some cool stuff with it. Where are you doing cool things with binder jetting? What industries does this apply to? The first one they kind of mentioned, which is medical. This is used a lot for dental implants, for things that need to be coated, but once they're coated with the post-processing, it doesn't really matter the strength profile or anything like that. So they use it a lot in dental applications. This is something that is used quite a bit in aerospace. You'll see a common theme, which is that pretty much all of these technologies are used all the time in aerospace. I think if these aerospace companies had their way, there would just be a hangar that was a 3D printer and it would just like print an entire plane and they could just fly it off, because pretty much everything is made with additive. With this binder jet technology though, what you'll find is that the mechanical properties are anisotropic or non-isotropic. I won't get too much into the details, but because you have layers bound together with glue, even if they've been sintered in the case of metal or fused in the case of the polymer, you're still going to have different, I'll say, breaking points, to keep it general, in different directions of the material. So this is not going to be used for loading necessarily. It is used for non-load bearing parts or aesthetic parts even. Speaking of which, one of the areas that this is used quite a bit is in furniture. So a lot of companies, furniture companies now, their industrial engineers will use binder jetting to either prototype a piece of furniture, or in the case of something that is not going to be holding up a whole room of people, they'll actually print the final part. Unfortunately, might be missing one or two industries, but without the slides, it's, the old memory banks get a little fuzzy when you get old. If you want to become involved, if you want to get a job working with binder jetting, and generally speaking, going forward, any of these technologies, there's going to be a couple of things that you'll need. So as I said earlier, 3D printing in general is a scalable thing. So if you have a 3D printer in your garage or in the lab at school, you already possess a skill set that you can put on your resume, right? Pretty cool. that is going to be translatable to a career that you could get doing any of these things. So what do you need though? Depends on what you want to do. If you want to get a job utilizing these technologies in any of the industries that I mentioned or will mention, it's going to kind of be dependent on what those jobs are also requiring of you in the other duties. Most of the time, it's going to be mechanical engineering. A lot of these technologies are tended to by mechanical engineers in these positions at these companies. You're prototyping, you're designing and printing parts, you're checking for tolerances, for loading, you're running simulations. If you have an electrical engineering background, especially when we get into additive manufacturing for electronics, you might be on staff to maintain the machines. These are complicated machines. They require a lot of control inputs from boards. They have a lot of motors. You also might be just a technician. You might be someone who is working on the machines to make sure that they function correctly. Now, what if you want to be building these machines, right? You want to work for X1, or you want to work for Stratasys, you want to work for Desktop Metal. That's going to require, more than likely, if you want to be on the R&D side, something more akin to a higher educational degree, a master's degree. I've seen some companies, when I was doing research for this, just straight out require a PhD, especially when you are in the more, the deeper side of R&D. But if you're not, you can also be working on teams, trying to get the stepper motors to run smoothly, or make sure that the assembly fits correctly. There's other jobs that you can have at these companies making these printers. So just keep that in mind as we go forward. I'll highlight the industries that some of these technologies are used in. Think to yourself, is that cool? Is that something I would want to do? Is that something that I would want to pursue? That is the wrong button. Okay, so moving on, if you need a strong part for an aircraft chassis or a hip replacement, something that is inside of a body, something that can't corrode or cultivate bacteria, or even a spacecraft, right? Something that is going to endure harsh environments, you're going to need something that's a little bit more robust than binder jetting. And the first one we'll talk about is digital metal laser sintering, DMLS. So this is going to use a rastering laser to selectively sinter metal powder in layers. Now there's something else, it's called selective laser melting, or SLM. The only difference between DMLS and SLM is that SLM actually melts the metal together. Digital metal laser sintering just fuses the powder, so it does not reach the melting point. The selective laser melting, is used for pure metals. So if you just want to fuse together a whole bunch of gold, or if you want to fuse together a whole bunch of just elemental titanium or something like that, there's use cases for that. For the sake of this presentation, we're just going to talk about DMLS. We're going to ignore some of the attributes we don't really need to worry about. So this technology is going to have some applications that you could just not do with other technologies. Specifically in the aerospace industry, I talked about how there were instances where the powder bed fusion, because of the materials properties and mechanical properties, you wouldn't necessarily want to have like a load-bearing member or a flexural member made out of something with binder jetting. You absolutely could with DMLS. You are going to find instances where this is used in tooling, especially in the forging industry, where you have these massive slabs of concrete metal that need to be moved around in a specific way. DMLS is going to be handy to make specific tooling for that. Touching on the SLM a little bit, I said you can fuse elemental metal. If you're a jeweler, if you're in the jewelry industry, you could actually use DMLS to make rings or other jewelry items. If you couldn't tell, I'm not a jewelry guy, so I just know rings. That's the one I know. The other thing you can do with metal is electron beam melting. Electron beam melting does actually melt the metal or the alloy. Get through this. There are pros and cons between the two. Suffice it to say that most companies, I think almost all, that create units for sale are doing DMLS. Most companies then, by transitive property, are offering DMLS services. So much so, in fact, that I couldn't even find an in situ video of electron beam melting. Suffice to say, know that these two exist. These are how you can fuse metal to make 3D parts. Let's talk a little bit about the industries. Same rules apply from before. If you want to get involved in actually R&D, creating these machines, similar, you're going to want to be looking at maybe having a higher education degree, maybe some experience with vacuum systems for EVM, some experience with laser systems for DMLS, and you're probably going to want to have a pretty solid materials science background, especially when it comes to looking at these systems that they're not quite melting the metal, they're fusing the metal. You have to worry about, will this work on different alloys? You have to actually spec out the density of the powder that can be used. You're worrying about things like, I have a bunch of powder sitting in a vat that is being essentially ablated. You have to worry about the enclosure. You have to worry about human health and safety when you're designing these systems. I will say, though, if you're looking around for jobs, you're not going to find EVM. This is almost outdated at this point. On the slide that would exist here, my computer didn't corrupt. I had a list of some companies that you could look for. If you just Google DMLS, you're going to get the top 4 or 5 companies are basically going to be the ones who SEO have decided are getting the most traffic. It won't be too hard to find them. I highly recommend looking at their jobs pages if you find this interesting. Some of them I did see are hiring for some additive engineer positions. And so those are the kind of positions you're going to find with these two, is additive engineers, chemicals engineers, a lot of even electronics engineers to work on the control boards and the different wiring harnesses with it. Okay, and then you might be thinking, cool, you can fuse metal. How about something a little lighter, like maybe a polymer? So SLS, which is selective laser sintering, is exactly that. It is basically DMLS, but for polymers. This has almost completely different use cases because it can fuse most polymers, or sinter most polymers, I should say, polyamides, polystyrene, thermoplastic elastomers, things that have different materials properties and serve different mechanical functions, right? If you need something that's going to be flexible, if you need something that's going to be lightweight, maybe you're using a generative design tool to come up with some cool honeycomb structures inside of, for example, motorsports. A lot of motorsports cars are looking at generative design with the sintered polymers to make super lightweight members for the racing cars. You would look toward SLS. So this technology is awesome. It's the fastest additive process if you care about things like speed when you're producing your parts. Unfortunately, though, it is not suitable for harsh conditions, even if you really treat it, because it's very porous, generally speaking, when you are done sintering the part. Same as before, if you want to be looking for positions, working with companies to actually produce these machines at the R&D level, it's going to be those higher degrees. From what I've seen, though, if you're just working as a manager or maybe a process engineer within the plants, a mechanical engineering degree, a chemical engineering degree. Actually, with these guys with the powder, you're also going to be looking at a hygienist, someone looking at the EHS impacts of having powder used in these systems. So if that's something you're interested in, I recommend checking these companies out. Same as before, give it a Google. I apologize for not having the top 5 list on here. The one thing, though, about these, if you're looking at it from a process standpoint, is the cleanup is atrocious. So I am going to share a video of the post-processing just to give you an idea of what it's like to clean up after one of these. And my call to action is someone, please, in the audience right now, invent a cleaner way of doing this so I can put one of these in my living room when they scale down to size. So here's what it looks like. I'm going to mute that awful stock music because it gives me a headache. So here you can see once the part has been sintered, it is still suspended in the workspace that's full of powder. So what this individual doing right now is he removed the parts from the powder. Now you actually have to clean all the work surfaces and all. That's a filter that he's sandblasting right now. But you do get a pretty cool fairly unique looking part out of it. I don't know what that's for, but just to give you an idea of the post-processing that's necessary. But you do get some cool parts. This guy's a little squishy. He's made out of some long chain polymer that is flexible. And then you can do some pretty cool coating. So these, looks like, I don't know, an impeller or something. These are coated with some kind of metal. I don't actually know, but it looks cool. It looks like it's a little bit more robust than your typical polymer. Okay, now we're getting into the UV polymerization path. From here, especially when you're looking for jobs that might be creating these machines or utilizing these machines, they are less prevalent than with FDM or powder bed fusion. And there's some reasons why. First, we're going to talk about material jetting. So material jetting is really, really cool. I am super stoked for when this scales. Basically, what you do is similar to binder jetting, is you actually will move across in one fell swoop with a liquid. But this liquid is a photopolymer. I'll talk about that more in a minute, but basically what it means is when it's hit with UV light, it hardens. It has a bunch of monomers, right? Monomers that are floating around, and as soon as UV light hits, they kind of go like that and they harden up. After the liquid is deposited, though, immediately after is a high intensity UV light, so it cures it right away. And what you get from this is an ultra fast process with dissolvable supports built in, because you can mix up what fluids come out of that print head, and you can do multicolored material right away. So here's an example of multi-material. This is some cover for some, I don't know, walkie-talkie or something. And then here is an example of multicoloring. This is without any post-processing whatsoever, maybe a little bit of polish on the external layer. Why isn't this everywhere? It's a good question. Why am I not going to tell you all of the different career paths and opportunities for jobs and stuff? Because it is just so expensive that no one is using it. The machines themselves are not that expensive. They're only about $30,000. I know that's not expensive, but the materials are stupid expensive. It's up to $1,000 per kilogram of material. So imagine passing that on to your customers. That's not really a value-added proposition to your services. It's because the IP right now is owned by Stratasys, and they sell all the resin. I think soon they might license that out to other companies, but for right now, not happening. So like I said, I'm not going to get into, oh, it's used in this and that industry. Right now, it's just kind of a tech demo, but it's very cool. Okay. Sorry, let me kind of skip past some of this stuff here. But it is important to point out that, like I said, these technologies are a little bit more hobbyist friendly. Like I said, if you want to start to build that resume, if you want to start to work with these technologies, especially if you're in high school, these are going to be what you can purchase yourself, set up in your living room, and start playing with. Let me find a good place to just pause for a second. So before I move on, I did have a couple awesome slides on additive manufacturing for electronics. IPC is a trade association and standards development organization for the electronics manufacturing industry. So of course, I wanted to talk about what it means to 3D print a printed circuit board. So what I'm going to do is on the fly, I'm probably just going to have to kind of give some visual aids here. So I'm going to let Nano Dimension take 50 seconds to talk about their Dragonfly machine. And this is what actually prints PCBs. So Nano Dimension is a company that has actually showcased their machines at IPC Apex before. It's exactly what it sounds like. It's a 3D printer for PCBs. So I will share this. Oh, it just started. That's nice.
Our Dragonfly 2020 3D printer is capable of depositing both electrically conductive and insulating materials, enabling designers and engineers to print fully functional electronics in-house in one print job. Companies are already using this multi-material solution to bring speed and efficiency to their development and manufacturing processes, reduce lead times and cost, and create opportunities for design innovation.
So it's exactly what it looks like. It is a printer that is capable of depositing conductive material and insulating material. And so what this does is it bypasses the usual masking and etching, the different stencil layers you need to put down to what is traditionally used, currently used to make electronic devices, PCBs. You can just bypass all of that. This is capable, from what I understand, of passive embedded devices, things like capacitors and resistors. However, it is also capable of some pretty sweet geometries. So let's say that you want to put an inductive loop in. You can just have it at any angle you want. Let's say that you want to have a really sensitive 3-axis sensor for something. It doesn't have to be X, Y, and Z. It can be any angle. So there's some really cool opportunities for electronics design within these printed additive manufactured PCBs. All right, so I really quickly want to go through FDM, which is fused deposition modeling. For the sake of this talk, I'm not really going to dwell on all of the physics and the chemistry, just because who really cares and we don't have a lot of time. So FDM, which is fused deposition modeling, use thermoplastics. In brief, thermoplastic, they become pliable at an elevated temperature and solidify upon cooling. Long-chain polymers, tensile strength, yield strength, they're non-Newtonian fluids. We don't need to worry about that right now. So FDM printers use filament. The thermoplastic is fed into the printer. Key to know is that there are so many different kinds of filaments now that serve so many different niches that all have materials properties that are suited to different applications. The most commonly used are going to be PLA and ABS, polylactic acid, and acrylonitrile butadiene styrene, I think. Yes, that's on the page. All right, rock and roll. I remember stuff. And they each have different use cases. PLA you're going to want to use for static loading, and ABS you're going to want to use for dynamic loading. That's basically what you need to remember. And here's just an example between the two. So something that I've saved until now, because it is true for all of these additive manufacturing technologies, is that just like a PCB needs to have a PCB designer actually do the work in an Altium or whatever before the PCB can be fabricated, obviously you need to have a CAD engineer that is doing the work before any part can be printed. A lot of the times that job, especially in a smaller company, is kind of rolled into a mechanical engineer's role. I know if there are any mechanical engineering students on the line, SolidWorks, am I right? Cool. Yeah, we're used to having to do the CAD work. But sometimes there are just dedicated CAD engineers at especially larger companies. Sometimes there are roles that are exclusively additive manufacturing engineers, like I mentioned earlier. All they do is they take the CAD file, they feed it into the machine, they post-process the print, they shove it off to metrology or tolerance or whatever, quality control. Regardless, though, you're probably going to want to know how to do some CAD work if you're working in additive manufacturing. At the very least, you're going to need to know how to work your way around at least the end stage. Maybe you just import a file and you export to STL, and then a slicing tool. For a hobbyist, I highly recommend Cura. When you get into the industrial level machines, they often come with a proprietary slicing tool that you'll use at work. Very quickly, FDM printer anatomy. This was built more for people who had never even seen a 3D printer before. The FDM printer has a 3-axis coordinates system, like most things in 3D space, I guess. Up, down, left, right, up, and down. And it prints just similar to the Yoda head we saw at the beginning. So different bed materials that you can use. Like I said, I'm not going to dwell too much on this just because I'm kind of running out of time. Suffice it to say that there's going to be different materials that you can use for your substrate depending on what you want to print. And then all sorts of troubleshooting that you have to do if things fail, which if anyone has just hit 3D printing on TikTok and watched the live feeds, like 90% of it is just string shooting out of a printer because no one knows how to tune their printer anymore. Most of it's due to workage. Drive type, I'm biased. I think a direct drive is the way to go. Aaron, I'm assuming we're handing out these slides, right? Afterwards, so I can just kind of rush through this. I don't want to take too much
Yeah,
time.
if you can share these, then we can absolutely send them out.
Absolutely. All right. Okay, let me just get through this and we'll stop and I'll talk about some opportunities for careers in. Okay, so FDM, fused deposition modeling, is everywhere. The SLS, the SNOT selective laser sintering, the shuttle launch, space launch system that NASA is working on, has a lot of 3D printed components everywhere. I think it was the Falcon Heavy had a 3D printed fuel tank, or I think maybe it was the oxidizer tank that was 3D printed. I could be wrong. I'm perfectly willing to be wrong on that. Point being, these things are showing up everywhere. But 3D printing, as I said, especially for these FDMs, is scalable. So something I want to bring up is work on these, get good with them, put them on your resume, get an awesome job. But also work with these things, put a couple in your garage, go onto Fiverr, sell your prints as services, right? There's different ways that you can make some side cash, especially if you're trying to put yourself through school using 3D printing. Just want to put that out there, maybe let that germinate in your minds if you want to make some side cash. Other areas where this is, it's all over the place. Bioprinting, actually printing out tissues using specific filaments that allow for stem cells to be cultured on them. You're going to see FDM a lot in construction now. A lot of consumer electronics are actually becoming printed. One thing that I failed to mention earlier is that Chanel just patented the first 3D printed mascara brush. So it's starting to really pop up everywhere. There's a picture of it. It looks awful, but at least it's 3D printed and they're taking a step, I guess. And finally, a more liquid approach, I'll get through this pretty quick, is going to be the SLA and DLP. So this is much more accessible for hobbyists than the other UV polymerization technologies. You have this is an Ellie Goo. This is actually what we have behind me in the blurry abyss. You're going to pull out of a vat, and every time you pull out, you're going to flash either an image of UV light for a digital light projection or a laser, a UV laser for stereolithography. It's really a difference between the two. Every time you pull out, you flash an image that corresponds to a layer. After 10 hours, you've got yourself a 3D object. So this is just the difference between, this is going to be DLP, and you can see in an SLA the laser rastering through. So just like with filament, there are more resins than there are atoms in the grains of sand on a beach. Don't need to dwell on it. Any use case, any application you can find a resin for. The only thing I will say, I have to mention this because I'm huge on human environmental safety, is this stuff is nasty. It is a VOC. It off gases volatile organic compounds, which can cause cancer. They're skin sensitizers and respiratory irritants. You have to wear a respirator and gloves. And it is incredibly harmful to aquatic life. You cannot dump this stuff down the drain. I would be remiss if I didn't bring that up. Now, with that scary stuff out of the way, I do recommend you pick one of these things up. They're very cool. All it takes is a little bit of common sense, respirator and gloves. Yeah. Okay. I'm not going to jump into this because I want to leave time for Q&A. Yeah, static image. Okay. Technically, the printers I have are called mask stereolithography. You can read the slides later. Not that big a deal. Does it matter? No. Okay. Lots of disposables and consumables for this kind of UV technology. In an industrial setting, you can imagine the resources one burns through when you have to clean tanks with isopropyl alcohol or chlorinated solvents as opposed to, little bottles of rubbing alcohol. So it's something to think about, especially if you get a job and you want to recommend a printing technology. You have to keep these things into account. Okay, and the last thing I'll say is, which do you use? As a hobbyist, it's not really going to matter too much if you want to print delicate miniatures, things with very fine detail. an SLA or a DLP printer or an MSLA is right for you. If you want to print more robust structural models, you know, like wire racks or drone chassis or like cosplay armor that you're going to be wearing for 10 hours at E3 or whatever, you're going to want to get an FDM printer. And there's other things that will influence your choice. Okay, finally, super quickly, I'll let you guys read these slides when I give them out. Just some recommendations for you before I go. For FDM printers, you cannot go wrong with Creality, cannot go wrong with an Ender. These are high quality, they are tried and true, they will not break on you. Monoprice is good, Anycubic is okay. For DLPs, or the MSLA, Anycubic, that's going to be what you want to get. But if you can't get one of those, Ellie Goo is the next best. They have a lot of models. They're kind of considered the king of lower middle consumer grade resin printing. And finally, here is something that I'm not allowed to share yet because it's a surprise. But the last thing I'll say is, if you're in high school, one of the best things you could do is start a 3D printing club, because a lot of school districts have funding for things like this. Talk to a teacher, put together a proposal and bring it to your department head, and then eventually the principal, and eventually wherever else it needs to go. It'd be very cool. You can get a few printers every couple of weeks, hang out with some friends, print some stuff. If you're in college, I can guarantee your physics or engineering department already has these things just like falling out of the ceiling. If you are not already involved in either I can't remember the name of mine when I was in grad school, but there was just like a room that just had like 15 printers and you could come and just print whatever you wanted. Get involved. And whatever any of you do, portfolio. If you print something that someone else has designed, cool. Take a picture of it, especially if it looks great. If you print something that you have designed as part of a project, as part of research, as I really wanted to hook this mini fridge up to a Mountain Dew dispenser and have it distributed throughout the house, and here's how I printed fasteners for that. Throw it to a portfolio, put it on a personal website, link to that in every resume you put together. Just has to be a link or QR code. It looks really cool, trust me. And the last thing I will say as far as career is concerned is, don't be afraid of how complicated some of these industrial machines look. Go in, be cool, be confident. All of these machines you can figure out, I promise. Okay, I'd say for improv in half of that turned out pretty good. So totally ready for some Q&A if there are any questions. I'd be more than happy to take a stab at them.
Awesome. Thanks, Patrick. I'll certainly, if anybody wants to post anything in the chat for Q&A, we were intending to wrap up at 3. We still can, depending on what questions we get. I think you already answered one that we got during the chat, but which process provides the finest detail?
Good question. Definitely any of the UV processes, specifically your SLA or your DLP, the digital light projection. But what I didn't necessarily mention is that those are going to be very brittle. A lot of the resins, when they cure, are very brittle. So as far as the finest for actual like application, probably the EBM, the electron beam melting, because that really isn't used that much. It'll probably be a tie between the digital metal or the SLS, depending on what material you want to use. Good question, though.
Okay, thanks. So we have an individual who raised their hand. I did unmute you, Jared, if you want to unmute and chat. If not, you're welcome to. Looks like we can hear you.
Oh, I apologize. I think I pocket waved.
Okay, no problem.
Yeah, I had to travel. Sorry.
No problem. Okay, we have just 2 minutes left. Any questions in the chat or Q&A?
I do see like bubble.
Oh, they are coming in. Oh, yep.
Yeah.
Feel free to take whatever you'd
Can I
like.
click on these? Oh, cool. I didn't know I could press that button. Neil asks, do you think 3D printing consumable fluids will ever become a reality? The answer is it already is. There's chocolate 3D printers. There are printers for foods that are relatively homogeneous, so it's like the same material. I think it's a niche thing. I think it's kind of like those coffee makers that print pictures with foam, bring them to conferences, show them off to your friends. But I don't really think it's going to be a huge thing. Maybe in a couple of years. You're going to pay a lot of money for the food, though. Paul asks, is the cost of materials for resin printer much higher than a filament? The resin itself is comparable to the filament, but the actual full process of post-processing your print with the resin printer is higher. You have to wash it. Some resins you have to wash in IPA. You need to cure it, which takes a curing oven that can cost money. The consumables are going to cost more in the long run with the resin. Which process is the fastest? Well, that's a good question. It depends on the size of the part. I think for general, like industrial scale, SLS is the fastest, which is for the polymers. If you're just printing at home, the DLP is going to be fastest, but it's going to depend on what you need or want to print. I'm just going to burn through these, Aaron. Tell me if we need to stop.
Go ahead. I'm just posting them in the chat so people can see them as well.
Anthony asks, what kind of filament would be best for printing parts for electronics? That's an interesting question. I'll answer both ways that I can interpret it. If you are actually printing the electronics, like the nano dimension folks are doing, conductive filament does exist for FDM. You can buy conductive filament. I have not heard anyone have any great success with it, but you can. So something that FDM printers have is dual or multiple extrusion. So more than one filament can be printed at once. So you could, in theory, print a very crude PCB with conductive filament. If you're talking about like housing and like assembly stuff, I would probably recommend based on your application. I mean, if it's going in the belly of a drone, definitely ABS. If it's going on a shelf, I don't know, PLA, doesn't really matter. All right. Okay, let me just make sure. Okay, thanks, Aaron. How about printing 3D house or apartment with cement plus fibers? Yeah, stuff is cool. Yeah, so you can print whole houses. They have these huge 3D printers. It's actually just like a gantry hooked up to a cement truck with specially formulated cement. Like you said, it's reinforced with fibers. I think actually now though, they might add the fibers in separately. Yeah, man, it's cool stuff. That's all I can say about it. It's very cool. I read somewhere the other day that it's running into issues scaling because of costs associated with actually making the cement, but the technology itself is proved. So it's cool stuff. Would you mind going into a bit more detail into the kind of printers best for electrical components, caps, inductors, etc.? Yeah, so similar to before, the kind of printers that are doing like what we saw the nano dimension folks do, it's a proprietary printer. That is not going to be something that you'll have at home anytime soon. But if you want to mess around with conductive filament, kind of, like I said, building your own PCBs, that's going to be an FDM printer. It's going to be a printer that like was printing the Yoda, and you're just going to use conductive filament and an insulative filament. Most of the plastics will be relatively insulative. You'd have to look at the dielectric strength of the plastics. I don't know this off the top of my head. And you just have to make sure that the voltages you're messing with, you have to be really careful. I would definitely keep it in the low voltage regime because you don't want to really worry about that dielectric breakdown, because none of these plastics, I think, are actually designed to be insulators. But with the caps and stuff, I mean, it's just going to depend on how you design the vias within your software. I mean, but it's all conductive filament. Don't plug it into mains power. Just don't do it. That's all I'll say. Or do it. I don't know. Just be really careful.
Okay. I think we're going to wrap up. We are a little bit over time, and I want to, make sure we stay on schedule here. We appreciate everybody coming out. If you do have more questions, I'm going to send a follow-up to everybody here with information about the slides and giveaways, and just a thanks for attending. So you have our contact information. I'll share Patrick's information if anybody wants to follow up with him directly and ask any other questions. Obviously, there's a lot of nitty-gritty details here. Patrick honestly said a lot of acronyms and things that I've never even heard of, so I hope some of you soaked in some of the valuable information. But thanks again, everybody, for joining us. Thanks, Patrick, for hosting today. And yeah, we look forward to seeing you next time. We do these events once a month, so the second Friday of each month. And hopefully we will see you next time.